Today we are going to talk about something called bag of visual words. Now, bag of visual words, we can use it for essentially converting images into vector embeddings or image embeddings, and using those image embeddings in image classification and image retrieval. Now, this video is going to be split into two parts. First part, we are going to look at the theory of bag of visual words and how it works. And then in the second half of the video, we'll actually look at an implementation of it and see how we can implement something like bag of visual words in Python. So let's get started with trying to understand what exactly is bag of visual words. Now, for those of you that are coming from NLP, you may have heard of bag of words before. It's a very common technique used in using NLP and information retrieval. But it focuses on sentences, it focuses on language and text. So we can pretty much visualize it as this. So we take a sentence and we pull out all of the individual words from that sentence, and then we put them into a bag. This bag is unordered, so imagine it's just like an unordered list. And that's what bag of words is. Bag of visual words is pretty much the same thing, but applied to images, which is quite interesting. So how does that possibly make sense? How do we extract words or visual words from an image? Well, at a very high level, it's pretty much what you can see here. So we take a load of images and we extract almost like patches from those images. And this is not exactly what happens. We don't just put those patches into a bag. We actually convert these patches into what are called the visual words. So these patches here, we would call visual features. And then we do some pre-processing in the middle here. You can't see it right now, but we'll fill all of that in throughout the video. And what we get out of that processing is a load of what we call visual words. Now, as with language, there are a limited number of visual words. Okay, there are so many words in the English language, and there are also so many visual words in our image datasets. Now, a visual feature, let's say this over here is a visual feature. It consists of two things. It consists of a key point and a descriptor. Now, key points are the points in an image that the visual feature is located at. So it's like the coordinates. And they do not change, or they should not change, as an image is rotated, scaled, or transformed in some way. And descriptors, as you might have guessed, are almost like a description of that particular visual feature. There are multiple algorithms for extracting these features and creating these descriptors. You can use algorithms like SIFT, ORB, or SURF. Now, we're not going to go into detail on what those algorithms are doing right now, at least, but we'll just understand that they are pretty much looking at these images. They're finding edges, changes in color, changes in light, and just identifying those and running those through a set algorithm to create what we call the descriptor. Now, the most common of these, and the one that we are going to use, is called SIFT. Now, SIFT is pretty useful because it's invariant to scale, rotation, translation, illumination, and blur to an extent. Of course, it's not perfect, but it can deal with all of these things. Now, SIFT first looks through the image and it identifies a key point, so something that it believes is of relevance. So just as one example, it will probably look up here, and there's not really anything in that image, right? There's no difference. It's just one flat color. So it probably won't extract a feature from here. Okay, but when it comes over here, it's going to see some edges, it's going to see some changes in color, and it's going to be like, okay, well, there's something there. So we put a key point there. And then it's going to go through all of its like algorithmic magic, and based on the edges, the colors, whatever else in that particular patch, it is going to produce a 128 dimensional vector. Now, it doesn't stop there. It doesn't just find the first patch. It goes through an image. It's going to find like a load of patches, especially for this image. There's a lot of information everywhere. It's going to be like, okay, look, there's a window, there's this edge over here, there's something interesting over here, there's all these colors and edges. Like, it's going to find these key points, these visual features everywhere throughout this image. And we'll actually see what these look like a little bit later on. So what we get is a load of these visual features. The order of those visual features doesn't matter. They're all just kind of placed or they're suspended in the air over here, okay? We can almost imagine there's like another bag here, which is our bag of visual features before it becomes a bag of visual words. So we're kind of at this point right now. So every image just becomes this massive, essentially an array with all these 128 dimensional SIFT vectors. Now, once we have pulled out all of our visual features from an image, we move on to the next step, which is how do we go from visual feature to visual word? Well, we have to use what's called a codebook. So a codebook is essentially, it's going to be like our vocabulary. If you come from NLP again, you'll recognize vocabulary is essentially like a big list of all the words in your data set. Okay, this codebook is going to be a big list of all of the visual words from our images. But of course, we don't have our visual words yet. We need to create them. So that's what we're going to do next. We're going to build our codebook, which is basically going to create all of our visual words at the same time. So how do we construct this codebook? Well, the idea is that we take a load of similar visual features and we actually cluster them together, and we get a centroid out of that cluster. Now, that centroid is what we would call a visual word. So we look at this image here, right? We on the left over here, these are visual features, right? We have multiple visual features. There's all these things that look kind of like a dog's nose from a slightly different position, but they pretty much look like super similar, okay? And what we do is we process all of these. We use k-means clustering, and we get a single centroid out of this cluster of points that all look very similar. Okay, so we go from, what is this? This is 5 128 dimensional visual features to 1 still 128 dimensional centroid or visual word. Okay, and we do that using k-means clustering. Now, this does not just happen for a single image. Okay, we actually feed in all of our images from our, let's call it a training data set. Okay, so we'll actually have loads and loads of these images, not just one. Okay, it's very, very bad drawing. And okay, we have like a dog's nose over here, but maybe we have another dog over here, another image of a dog, and he has a nose, obviously, maybe. So these centroids here are also going to be very similar to the centroids of this other dog's nose that are over here. So in reality, we don't just have these 5 visual features that create our single cluster over here, our dog nose visual word. We actually probably have quite a lot. So that's the process of creating a codebook. We basically go through all of the visual features that we create. We're going to create a lot of them, and we compress them into a set of particular points, which become our visual words. Now, this process is called vector quantization. It's where you take a whole range of vectors, and you do something like clustering in order to convert this massive range of vectors into just a select few vectors. Okay, so again, we can use the example or the parallel of language. There are pretty much an infinite number of sentences out there in the world. But if we perform bag of words, we extract every word from, let's stick with the English language sentences at the moment. If we extract every single word and we put them all in a bag and we remove all duplicates, we're going to end up with far less than an infinite number of items there, right? That's quantization, I suppose, quantization of language. We're going from an infinite number of possible sentences to a limited number of possible words that make up those sentences. That's exactly what we're doing here. Okay, so just taking this one example, we have like a church building. Over on the left, we have these two visual features, right? These two dots, they're visual features. Maybe we can also have another visual feature over here, right? All of those should kind of be very similar. They're like this green window. You have all these similar edges and similar colors. So they probably all end up being clustered together into this single visual word, which is, a window. This one over here, right? We have this kind of like bell tower thing, and we just take different parts of this bell tower, and they would probably all feed into a single visual word. Now, one thing I should point out here is this is just one image. Now, imagine we took another image with other windows inside it. That other image with windows, let's say the window is here, we would take the visual features from that, and they would also be translated into this over here. So what we get out of that is, rather than our image being represented by all of these 128 dimensional visual features, they are actually represented by these technically 128 dimensional visual words, but because there's a limited number of these visual words, we can number them. So for example, this one would be 0, this one we selected here would be 1, 2, 3, and 4. And let's for now pretend this is our entire codebook. That means that this image here would now be represented by the number of visual words that we found, so the frequency of these visual words. So at position 0, we have a dog's nose. We didn't see any of those in this image, so that would be 0. This number 1 here, so we found like these two visual features over here, another one here, so we found 4 of these, right? So then this would become 4, okay? Again, we don't have like I think it's a dog's leg there. In this case, we found 2 of these features. So this is this one we selected here. And then here we have 0 again. Okay. So what we've done just there is we've gone from this representing this image with a very large number of visual features. So 128 dimensional. And also there were 6 of them in this image. In reality, there'd be a lot more. Okay. So quite a few values there. And then we've kind of compressed it down into this 5-dimensional sparse vector. Now, in reality, we're not going to just have 5 possible visual words. In the later examples, we're going to use around 200 visual words to represent just over 9,000 images. Okay, but that's still a big improvement over what we're doing here. So this massive matrix that we have has now just been translated into a 200-dimensional vector. And as well, I should say, the images that we take later, when we actually process, for example, this image, we won't just get around 6 visual features. We'll get more like, let's say, 800 visual features. So in reality, it'd be something like this, 128 dimensions, and then we would compress that down into a single 200-dimensional vector. Okay, that's what we're going to do. Now, if we consider, okay, how is this useful to us? So we're going to focus on, the information retrieval side of things, but it works as well with image classification, where we basically look at, so for now, we're going to add another step in a moment, but for now, we're creating, what are these frequency vectors? So this thing that you saw here, it's a frequency vector. And that frequency vector is basically telling us, okay, we have, we have this many. I'm just going to use this example. This is, I think, 2 or something like that. We have 2 windows in this image. In this image, we also have these 2 crosses on top of a bell tower. Whereas this image of a dog, we have a nose, we have a leg, we have an ear, right? So if you were to plot these in a high dimensional space, we'll just, for the sake of simplicity, we'll pretend, okay, this is actually a 2-dimensional vector. So our dog image could be like here, okay? And our church image could be over here. Now, they're not similar, okay? We'll use cosine similarity, so that basically means we're going to measure the angle between vectors. So if maybe we had another dog image, and because it has many of the similar visual words, it will be plotted in a similar space, in a similar vector space. So that means that the angle between these 2 here will be a lot smaller, right? When you compare it to the angle between either of those and this one here, okay? And then we're going to calculate cosine similarity between them, and we'll see that the cosine similarity between our more similar images with similar visual words, they are more similar. Okay, so we have our sparse vectors, but this is, there's another step that we need to take, and I'll return to the language example. In language, in NLP, we have something called stop words. Now, stop words are basically super common words that don't really tell you much about what it is you're looking at. So the word the, or the word a, the word and, all of these words appear in language all over the place, but they don't necessarily tell you what the topic of whatever it is you're talking about is. Okay? And in natural language processing, these stop words can be overpowering. That you can get 200 instances of the in an article, and if, for example, you are reading an article about like Roman history, you want to be looking for things like the word Rome, or the word Julius Caesar, or the words Julius and Caesar. You don't want to be looking for the word the. It doesn't tell you anything. So these stop words are usually, they're either removed from your sentences, or we can use something called TF-IDF, which allows us to look at the relevance of words based on how common they are across different documents. So in the example I just mentioned, we let's say we have articles about a lot of different things. And one of those happens to be this Roman history article, and it has the words Rome in it. Right. So as a user, when I'm searching, imagine I search something like the history of Rome. Right. So we have the history of Rome. 4 words there. When we're searching, we don't want to give equal relevance to the word the as we do to Rome, and we don't want to give equal relevance to the word of as we do to history, right? We basically want to just ignore of and ignore the and just focus on Rome and history, right? So TF-IDF allows us to do that by looking at the frequency of words across all these different documents and basically scaling the score of the frequency scores that we've just retrieved based on the frequency of these words throughout all your other documents. And the same is possible with visual words. So we have all of our images, they are the documents, and we have all the visual words in all of those images. We use TF-IDF to look at the visual words found in each frequency vector, and we use that to essentially lower the score of visual words that appear all the time and increase the score of visual words that are very rare and very unique to a particular image. So in the church image that you see here, in a lot of cases, SIFT isn't going to pick up patch number 1, but let's say it did in this example. So it's picked up a patch of sky. A patch of sky is probably pretty common in a lot of pictures. So we would want to bring the score of that patch of sky down. We'd want to lower it. Whereas this patch number 2, we want the score of that to be increased, or at least just maintained. Okay? So this is how we do that. This is a typical TF-IDF formula. Now, TF-IDF typically, we think of it with documents and terms, which is just words. So the notation, maybe it's a bit weird to translate over into images here, but we'll do it anyway. T refers to term in typical TF-IDF lingo, but we are using it to represent visual word. D usually means document. In this case, our documents are images, so it's an image. Okay, and then we have TF, TD, and that refers to the term frequency of the frequency of a particular visual word in a particular image. Okay, so the frequency or term frequency of visual word in image. Okay, let's say we took over here we have visual word 1. So TF of visual word 1 in image, we'll call this image like image 0. In image 0 would be equal to 2. Okay, because there are 2 of these patches, or if we want to include the other ones, it would actually be 4. N that you can see over here, that is the total number of images. So number of images. DF, T here, so that stands for document frequency of term. So essentially, how many documents does our particular visual word appear in, or how many images does our visual word appear in? And all of this is, so we take both of those and we take the log of them. Okay, so this here becomes this is the inverse document frequency. This whole sort of part here. This is the term frequency. We multiply those together and we get this, and that gives us the TF-IDF. Now, the IDF part, if you look at this, so just consider this, it's useful to understand. We have a number of images. Number of images does not change based on which image you're looking at. And the document frequency for a particular term, that also does not change depending on whether you're looking at a particular image or not. So this IDF vector is actually the same across our entire data set. Okay, it is not going to change. The only thing that changes is the TF-IDF, which is the term frequency. So using this, we can go from what we have here. So all of these visual words are kind of on the same level. There's not really any variation there. To something more like this. So maybe we've decided that a nose is a pretty good indicator of something relevant. Okay, whereas like this leg thing here, it's not a very good indicator of anything. Okay, so they've been adjusted in accordance with their relevance. Okay, so we've just been through how to create our visual words, how to create it's like a sparse vector representation of our images based on those visual words, and then how to scale the values in those sparse vectors based on the relevance of each visual word that the values represent. So after we've done all of that, we're sort of ready to move on to the next step, which maybe you want to feed all of these vector representations into a classifier model in order to perform some classification, or what we're going to go through is how we can actually retrieve similar images based on these vectors. Now, there are different distance or similarity metrics that we can use when we're comparing vectors. You have dot product similarity, you have Euclidean distance, but we're going to focus on using cosine similarity. Now, this is really useful because the TF-IDF scores that we've output here, the magnitude of those vectors can vary significantly. So by using cosine similarity, it means that we don't need to normalize anything. So we can just take these vectors and we can compare them immediately, which is really useful. So cosine similarity is calculated like this. So let's say I'm going to draw another one of these 2D graphs, right? Let's say we have vector A here and we have vector B over here. Okay, the dot product on the top here, this is going to increase as these two vectors are more similar. But that by itself, this dot product value, it works poorly when we have other vectors of different magnitude in here. So if we had all these different vectors, let's say we had one over here, although we might say that we're going to call this one C, I'm going to call this one D. To me, it seems like B and C are probably more similar than C and D, but because D and C have a greater magnitude, the dot product, which considers both angle and magnitude, is going to produce a higher score. Okay, and that's even true if maybe, let's say we had like B in another item here. Even though these are basically the same vector, they would score lower than D and C, purely because D and C have a larger magnitude. Okay, so what we do is we add this item here, which looks at the magnitude of A and B together, and we divide by that. So we're essentially normalizing everything in this calculation. And that's how we calculate the cosine here. So we're actually just calculating the cosine between angles, okay? And that gives us our cosine similarity. So let's just have a look at another example. So here, if we had two exactly matching vectors, the cosine similarity between those would be equal to 1. If we had two vectors that were at a 90-degree angle, so vector A is perpendicular to vector B, we would return a value of 0. Now, because we're using TF-IDF, all of our vector values are positive. So in reality, all of our vectors would have to be placed within this space here. So within I'm assuming this is the positive of the y-axis, and this is the positive of the x-axis. So all of our vectors would actually appear in this space here. So this vector A down here would not happen, but just using it for the sake of showing you that we can have a cosine similarity of 0. Now, in this image here, I'm just trying to point out the fact, okay, again, it's the same thing. Where we have two images that are exactly the same, okay, so these appear in the middle here, the cosine similarity for those is going to be 1, okay, and here and here. This image, there's like a building in the background, there's some trees, so it's kind of maybe halfway in between the church image and the dog image. Now, because the dog image has some trees, the church image has some, it's a building, so it shares some similarities, both of them, with this image. So it would probably be somewhere in the middle of that similarity scale. Okay, somewhere around here. And then images like the church and the dog, there's not really any similarity there, so they have a lower, closer to 0 cosine similarity. Okay, so that is the theory behind bag of visual words and how we actually retrieve similar images using bag of visual words. Now, like I said, there are 2 parts to this video. Now we're on to the second part, which is where we're going to have a look at the implementation of all of this in Python. Now, if you want to follow along with this, there will be a link to a Colab notebook with all of this in the description, or if you're reading this on Pinecone, in the resources at the bottom of the article. So what we first need to consider, okay, we need a data set of images. So we're going to keep this super quick, light, and simple. First, we get we're not uploading, so we download the Hugging Face dataset. We're using this one, so it's like what they describe it as a French ImageNet. I'm not sure what makes it French, but it's just how they have they've described this. But it's almost 10,000 pretty high resolution images that we can just download immediately. Like, this is all we do, and we can see straight away we have that church image. Okay, and yeah, we can see all the images just by printing them like this. So first thing we want to do is translate these images. So these are what are called pill image objects at the moment. We want to translate those into NumPy arrays. So we can do that. We just go through the entire data set and we create this array, or this list, sorry, of items, which is going to be a list of NumPy array versions of our pill objects. Now, these images, some of them are grayscale, some of them are color. We're going to drop the color from these images and we're just going to have grayscale. So we can do that here. So we use the OpenCV library. Okay. And we just go through and we convert all of these images, if they are RGB images, to grayscale. If they're already grayscale, we don't need to transform them. Now, how do we tell if they're grayscale or not? Well, the shape of an image that is grayscale is different. So let me show you images. Okay, so we see here that we have this two-dimensional array. Okay, whereas if we had a look at so in images training, these are all the color images that we still have. If we have a look at beforehand, it's a three-dimensional image because you also have the red, green, and blue color channels included in that array. So that's how we can tell. That's why the length of the image shape here. When it is 2, we know that if it's greater than 2, sorry, we know that it is a red RGB image, whereas if not, it's grayscale. So we can see, okay, these are the new grayscale images. Now the next step, now that we have our images and they're ready, they're pre-processed, we need to go through that process of creating eventually creating our sparse vectors. So we start by creating the visual features. Then we move on to visual words. Then we create the frequency vectors, and then we create the TF-IDF vectors. Okay, so number 1, visual features. We do that like so. So it's actually pretty simple. We are using SIFT from OpenCV, and what we're doing here is just initializing lists where we're going to store all of our key points and descriptors. So remember, we had both. The key point is kind of pointing to where the visual feature is, and the descriptor is a description of the visual feature, 128 dimensional vector. And yeah, so we initialize this extractor, the SIFT extractor, and here we're just, for every image in our black and white images we're going through, we're extracting the key points and the descriptors, and we're adding those key points and descriptors to our big list of key points and descriptors here. Now, you will notice that we're doing this image by image. So in here, we're actually going to have, so for example, the descriptors, we're going to have, maybe I'll show you in a moment actually. I'm sure I will show you later. Why don't I show you now? So let's have a look at descriptors for, I don't know, say image 100. We have a look at the shape. So for image 100, you see that we have 436 descriptors. And each of those descriptors is of dimensionality 128 because it's a SIF descriptor. Okay. Now, this won't happen with this sample, but just be aware that some images, for example, imagine you have like a picture of the sky and there's not really anything there, it's just like the color of the sky. The SIFT algorithm might just return nothing because there's nothing for it to, there's no key points for it to look at. There's like no change, just a flat image. In that case, the image, the SIFT descriptors will just be none. So we have to be careful in the next step and just avoid those. So that's what we're doing here. If there are no descriptors in a particular image descriptor list, we just drop it. We just drop that image. Okay. But for this sample, it's not really a problem, but just letting you know, because in other data sets, you might come into this problem. Okay. So, yeah, all we're doing now, we're just dropping any of those descriptors that don't have any of those images that don't have any descriptors. As I said, not an issue for this sample. Now, let's have a look at what these key points and descriptors actually look like. So these here, so these are all the key points. So in the middle of each of these circles, we have a descriptor. Okay, so we have the SIFT algorithm has identified a visual feature in each one of these circles. Okay, and we can see here and here and so on. All right. So the center of these circles is the position of the key point. The line that you can see is like the direction of the feature that was detected. And the size of the circles are essentially like the scale of the feature that was detected. So with we have all of our visual features now. Remember in that list we had visual features, visual words, frequency vectors, and TF-IDF vectors. Now we're on to the visual words part. So first, all we're doing is creating 1,000 random items, we're going to use this to select 1,000 random images. We've added this random seed in here so you can reproduce what we do here. Now, the reason that we are taking a sample in the first place is just to speed up the k-means part of this, the training part. You can leave this if you want and just train everything. It will take longer. So we extract the descriptors and the key points for our training sample, and we put everything together. All the descriptors. When we're training k-means, we don't care which image a descriptor is in. All we care is that the descriptors are there. So we take all of our descriptors and we put them all into a single NumPy array. We can check the shape. So we have, is it 1.1 million of these descriptors? It's quite a lot. For less than 10,000 images, I think it's fairly large. And yeah, so here I'm just showing you, okay, number of descriptors contained in each image. Each image. So we have like image 0 here. It has 544 descriptors. Second one, quite a lot more, quite a lot less, and so on. It's kind of, each image has a different set of items in it, so it's normal. Now, you have to set the number of visual words that you would like from your images. So it's like the vocab size in NLP terms, NLP lingo. For this, I just set k equal to 200. So we're going to have 200 visual words from this. We don't have that many images, if you have more images, you should probably increase this, particularly if they're very varied in what they are. If they are not varied, they're all kind of like the same thing, you can probably use less visual words. And yeah, so we are performing k-means here. We just do it for one iteration, and that outputs our codebook, which is essentially just a big list of all of our clusters. Now, if you are, I don't know, maybe you're creating your codebook on a machine, and then you're going to be using it later on, like over and over again, I figured it's probably pretty important to show you how to actually save and load that codebook. It's pretty easy anyway. It's not like it's difficult. So we use joblib here, and we just dump k, which is the number of visual words that we have. You don't even necessarily need to put that in there. You could just use the codebook alone, and we're going to save it into this pickle file. And then when you're loading it at a later point, we just use joblib load. There's nothing else to it. Now at this point we've constructed our codebook. So we've created our visual features, we've created our visual words, and they're all just stored in this codebook. And now what we want to do is take the visual features from our images, process them through the visual words that we have in our codebook, and use that to create our sparse frequency vector. So that's what we are doing here. So we go through each of our images in descriptors, or the set of descriptors, image descriptors in descriptors. And what we do is we use the vector quantization function from SciPy to extract the visual words from those. And what that's going to do, it's not going to extract the actual, like the vectors of the visual words. It's going to extract the IDs of the visual words. So we actually get all of these ID values, each of which represents one of our visual words. It's like a token, right? In NLP, you have word tokens. In Bag of Visual Words, you have visual word tokens. So that's what we have here. Okay, so in image 0, we know that the first 5 of our visual words have these tokens. Okay, so number 84, 22, and so on. And in total, there are 397 visual words in image 0. Okay, now this here, so we can take a look at the centroid, so the vector of the visual word, by looking at the codebook. We go to visual word, or use visual word ID or index 84, and we can see the shape of that is 128. Okay, that's like our centroid position. Now, how do we do we need to do like a frequency count. So how many of each visual word, based on the visual word IDs, how many of those are in each image? Okay, so we know that the length, so let's have a look at the length of our codebook, should be 200. Okay, so what we're going to do here is we're going to create a frequency vector. Each one of these is going to be of dimensionality 200, because that's all the possible visual words within our codebook. Okay, so we're going to loop through all of our visual words, and we're going to initialize the frequency vector for each image, and then we're going to loop through each word found in the image's visual words. And for each one of those visual word index values, we use that to add a 1 in the position of that visual word in the image's frequency vector. Okay, after we've done all of that, we have a single frequency vector for every single image, each one of dimensionality 200, and at the end here we're just reformatting that big list of NumPy vectors into a single NumPy array. Okay, and at the end we can see that we have 9,469 of these frequency vectors, each one dimensionality 200, aligning to our codebook. Now, from above, we saw that we had these visual word tokens in image, I think image 0. Yeah. So we had these visual word tokens. You can see we have 172 twice here. Okay, because that visual word appears in the image more than once. So let's go down here and let's have a look at each one of those. So actually, I don't know why I needed to count. I just copy and pasted it across. So we can actually even remove that if we want, but I'll just leave it. So if we have a look at those, we would expect all of these values to have at least a value of 1 because we've already seen that they are there. And for 172, we know there's at least 2 of them in there. And we can see that here. So we look at the position frequency vector 0. We look at each one of these positions and we can see that there are numbers there. Okay, and let's have a look at more of image 0's frequency vector. So we have this here. We can increase this. We can show everything, I mean. So we have this, 200 values. Each of these are the frequency of those visual words in that image. And we can represent that in a big histogram like this. Okay. Now we want to move on to the TF-IDF part. So, we have all of these frequency counts in a big vector, but some of those visual words are irrelevant. They're like the vision equivalent of the word the, or the word a, or the word and. We don't want those in there. They're not important. They don't tell us anything. So we use TF-IDF to reduce the score of those items, reduce their sort of dominance in our frequency vectors. So we are going to use the TF-IDF formula that you can see here. So first, we want to calculate, well, n we already know. It's the number of images, e.g. the size of the data set. And then df is the number of images that a visual word actually appears in. Okay. So basically what we're doing here is we're looking at all of the frequency vectors and we're saying, okay, if there is in a single vector, if the value is greater than 0, e.g. 1 or more, e.g. that visual word appears in that particular image, we will assign that position 1. Okay. And then we take the sum across all of those frequency vectors along the 0 axis. So basically, let's say we have visual word 0 in image 0. Maybe that visual word is the frequency is 3. In image 1, the frequency is 2, and in image 3, the frequency is 0. If we perform this operation across those 3 frequency vectors, the value in that from that first column would be equal to 2 because it only appears, it is only not 0 in 2 of the 3 images or frequency vectors. Okay, so we can see what's happening here. So DF shape, it's still going to be the same. We are going like we have the 200 dimensionalized frequency vectors. We have 9,000 of those, and we're compressing those 9,000 into a single. I don't know what we call this, like the DF vector. Okay, now let's have a look at this. So the inverse document frequency, I suppose we could call it the inverse image frequency, is just the log of n over df. Okay, nothing special there. And then to calculate TF-IDF, we also need the term frequency part of TF-IDF. Now, the term frequency part, we actually already have. Those frequency vectors that we've been building, they are the term frequencies. So that's all we do. It is the frequency vectors multiplied by IDF. IDF, by the way, we can see here, it's just a single vector for all of our entire data set. Okay, the only part that changes is the frequency vectors. Okay, and we get this. Now, if we plot that, you can see now this is the same image as before. So if we go up, you see that we had all of these like kind of high values. Now we come here, and there's just this this really high value here, maybe that's a visual word of the cross on top of the church. That's probably like a distinguishing feature if we're looking for religious buildings or churches or something along those lines. Whereas the rest of the visual words kind of get pushed down because most visual words are probably not going to be that relevant. Okay, now we've generated our TF-IDF vectors here. Okay, so we have them all stored in TF-IDF here. I'll just point out here we have just over 9,000 of those. And we can begin searching. So to search, we're going to use cosine similarity. So we're going to start with this image of a dog to start. Cosine similarity we calculate like this. Now we're going to search through the entire search space for B. So in this case, B is not going to be a vector. And we're just going to calculate the cosine similarity for all of the items when compared to A. So one of those items is going to be the exact match to A because A for search I, so maybe search I is, 6595. That image is still within B here. So we're going to get, at least at the top, we're going to get that image returned to us first. Okay. So the minimum and maximum cosine similarity is 0 to pretty much 1. We're using floating point numbers, so it's not actually exactly 1, but it's basically 1. Okay, I'm going to go quite quickly through this. So we use NumPy argsort to get the most similar items. The first image should obviously correspond to the image itself. We'd expect the cosine similarity to be pretty much 1. And yeah, that's what we get here. So we're going to just display a few of those. So using this as our search term, we get, this was our search term. Now this is the first result. Cosine similarity is equal to 1. We go down, we get another dog, pretty similar looking. We get this, it's not always perfect. And then we get more of these very similar looking dogs here. Okay. Now, that looks pretty good, so we're going to test through a few more images. We have this one here. It's like some old record player. First, we get the same record player. And I don't think this record player actually appears again in this data set, but I thought it was interesting because we get this printer. I assume it's a printer that looks very similar. It has this like bit on top, and despite the background being very different, and this one's just like an image, like a blurry image, it manages to pull through this object that to me looks pretty similar. And then the rest of them is nothing of relevance. Maybe this one's like a box, it's kind of similar. Okay, this one, we search for the sky with a fish. Obviously we get the exact image back first, and then we get the same guy with a fish in a slightly different position. It's like open his mouth a little bit. As you go to the side, then we get another guy with a fish. And then here, I thought this was kind of interesting. So here, okay, there's no guy with a fish. But you look at the background of these images, right? The background of these images is like some like leafy foresty place. And obviously here, leafy foresty place. So it kind of makes sense that it would pull through this image here as well. For this one, I suppose there's kind of like a forest in the background, but otherwise I don't know why this one is being pulled through. This one I thought was interesting. So this one it didn't perform well on, or at least it didn't return what I would expect it to return. Okay, so we have these two parachutists, and then we get golf balls, a dog, another golf ball. But if you look at this parachute here, it has this like really thick black line, and then the rest of the parachute is probably white. And here on this golf ball, you have like a very similar black line. So I assume for these golf balls, it's actually seen that and been like, okay, they're two very similar features. We have another one here. We have another golf ball. Return obviously the same one again, and then return another golf ball. Like another golf ball, same brand as well. And knees as well. And then we return this truck. I thought maybe the reason it's returning this truck is it has like this white ridge pattern on it, which the golf balls also have a similar sort of white ridge pattern. I wasn't too sure. But anyway, that one performed pretty well, I thought. This one, we have this garbage truck. The garbage truck here, obviously we return the garbage truck, and then we return this image. And initially I thought, okay, it's not very good. First result back, but then we get a garbage image here. But then if you actually look at this image, you look in the background, there actually does seem to be a garbage truck here. It's either a garbage truck or like some big industrial bin. I'm not really sure. But I thought that was kind of cool that it picked up on this thing in the background that I missed the first time I looked at this as well. So that's cool. But yeah, so there are all the results. I thought we'd go through those quickly to have a look at how it did. And you can probably optimize this to be much better than what I have here. We use a very small data set, for example. But we've done something pretty cool. I suppose we used k-means, so it's learned a little bit there in terms of the visual words, but otherwise it's very simple. Okay, and for me to see this sort of performance on without like some big neural network or anything, I think it's pretty cool. So I hope this has been useful. Thank you very much for watching, and I will see you again in the next one. Bye.